In this lesson, we will continue with our discussion of rotational motion, and primarily we will discuss what is the cause of rotation. Well, what is the cause of linear motion? We know that a net force acting on an object will produce an acceleration. That is the cause of linear motion. In the same way, what is it that makes an object rotate? Now, I'm going to produce rotation on this object. Now, this is the object on which I'm going to produce rotation. You can see I am producing rotation. All right, tell me, what is the cause of this rotation? Well, I know most of you will tell me it is a force. Yes, of course, I am applying a force. But a linear force that we are familiar with in previous lessons is not what is happening here. Now, the force I am applying is producing what you call a torque. Therefore, what makes an object to rotate is a torque. Now, I will write down that in a minute, but let's talk about this. So, what is the cause of rotation? The cause of rotation is a torque. Now, what is torque? Torque is caused by a force. Now, suppose I want to produce rotation on this object. If I apply a force directed downward, you can see that directed downward force is going to rotate the object, producing rotation. Now, when the object is here, if I apply a force downward on it, will that force produce rotation? No. So there are a couple of things that you need to understand about rotation. First of all, a rotation always occurs about an axis. Now, what is the axis of rotation of this object? The axis of rotation, let me see if I can show that to you. Now, this is the axis of rotation. You see that? This object is now rotating about this axis. In other words, the axis of rotation is at right angles to the plane of rotation. Now, if I want to produce a rotation about this axis and I'm applying a force at right angles here, the torque produced by this force depends on this distance. You see, if I apply the force very close to the axis here, will it produce any rotation on this? Very little. And finally, if I apply a force here on the axis, will it produce any rotation? No, it is not producing any rotation. So, the torque, the rotation effect, which is we call the torque. The torque depends on two things. One, the amount of force and the perpendicular distance between the force and the axis of rotation. Again, if this is the axis of rotation and the force is directed downward, the perpendicular distance between the force and the axis of rotation is this distance, and this distance is called the torque arm. All right, now tell me, if I have the object in this position and I'm applying a force downward and I'm rotating the object about this axis, well, what is my torque arm now? The force is vertically downward. Is my torque arm this distance? No. My torque arm now is this distance. In other words, if you consider a vertical axis there, the perpendicular distance between the direction of the force and that vertical, this is now the torque arm. If this distance is r, this will be now r sine theta, where theta is this angle. Now that means as this object comes closer and closer, what is happening to the torque arm now? The torque arm now is decreasing. That means when the object is here, the force that is directed downward will produce no torque at all. The torque arm is now 0. But now if I move it now like this, the torque arm is increasing. This distance is increasing. And when it is at 90 degrees, this is my torque arm. So there are two things that determines the torque when a rotation takes place. What are the two things? The two things are, one, the amount of force, the other is the torque arm. Alright, let's put that down in writing. I think I took more than. As we discussed earlier, a linear acceleration A is caused by a net force F net. The second law of motion is equally applicable to rotational motion. Rotational acceleration alpha is caused by a net torque. And we write torque, represent torque by the Greek letter tau. Let me write that for you. Now, tau is written like this. Pronounce it tau. So, the rotational acceleration alpha is caused by a torque, tau. Now, you are familiar with this situation. Here you have a screw. If you want to rotate that screw, you have to apply a torque. Now, I have a lever here which I can put into the groove and then turn the screw. A force F applied at right angles to the handle of the screw produces a rotation on the screw about an axis. What is the axis of rotation? Look at the axis of rotation. So just like I just demonstrated, the screw is now rotating about this axis. And now the force is applied at right angles to the handle. The perpendicular distance between the force F and the axis of rotation is this r. This is the perpendicular distance between the force and the axis of rotation. And I told you that that distance is called the torque arm. Okay? The torque tau produced by the force F about the axis of rotation is tau equal to r times F, the torque arm multiplied by that force. And that is a measure of the torque. Well, r is called the torque arm. Actually, the torque arm is a vector. This r is a vector. The force F also is a vector. Therefore, r times F is the product of two vectors. Now, do you remember in few classes ago, 2 or 3 classes ago, we multiplied two vectors to produce work done. Work done by A force is the product of the force and the displacement it produces. Force is a vector quantity, displacement is a vector quantity, therefore work done is the product of two vectors. And we call that product by a name. What was that? It is called the dot product. Now here, this tau is the product of two vectors. Now there is a difference between this product vector and the product vector we considered earlier, because work done is a scalar quantity. We found earlier that force vector multiplied by the displacement vector gives you work done, which is a scalar, and we call it the scalar product or the dot product. But the torque of a force is a vector. So the vector r multiplied by vector f is the torque, which is a vector. So this is called the vector product of two vectors, or sometimes called the cross product. Now, so r is a vector drawn from the axis of rotation, and f is also a vector. What happens if the force F makes an angle theta with the vector r? Now, if this force now makes an angle theta with the vector r, then you can see this r is no longer perpendicular to the force. Now, in order that this definition may be true, r and f has to be at right angles. The force must be at right angles to the torque arm. But if this f makes an angle theta, then the torque is produced not by the whole of this force, but the component of the force at right angles to the torque arm. Tell me, if the force vector makes an angle theta with the torque arm vector, what is the component of this f at right angles to that torque arm? It will be f sine theta. I hope you understand that. Yes. Now the component of this force at right angles to r is f sine theta. That's right. That means the torque is now produced by this component of the force. So what is the torque now? The torque now is r times f sine theta. So this is a general equation you can remember. When theta equal to 0, you see, when theta equal to 90 degrees, tau equal to r times f. In other words, sine 90 is 1. If theta equal to 0, that means the force and the torque arm are in the same direction. The angle between them is 0. That means that force cannot produce a rotation. Now tell me, why is the door handle kept away from the hinges of the door? When you pull on the door handle, do you see the door rotates? And what is the axis of rotation? It's the axis passing through the hinges. Have you ever tried to open a door by applying a force on the hinges? Will the door open? No. Why not? Because this angle theta is 0. The torque arm is 0. That force cannot produce a torque. So you must understand, torque is measured as the perpendicular component of the force. Perpendicular to what? Perpendicular to the torque arm. The torque of a force is the product of the torque arm and the component of the force at right angles to the torque arm. So what is the unit for measuring torque? Torque